Hello, and welcome to day 31 of learning ML from chatgpt. So let's get started. In today's video, we're going to be recapping days 11 to 15 of the ML series. So let's get started. So in this day 11, we learned about convolutional neural networks. So this is mainly used for image detection and object detection images. So first of all, we use a CFAR10 dataset, which is a bunch of images like boats. I think there's toads. It's a bit random, but they're quite different, so it's easy to differentiate. So X train, Y train, X test, Y test, which we can just do by calling load data, and then we're converting the pixel values into a range 0 to 1, which is what we normally do, as we saw in the data preparation part lesson. So we create a sequential model, and it's just like we did before, passing in an array. So here we have 2D convolutional neural network with 32 filters and 3x3 kernels. So this means we have 32 different filters. So a filter is basically something that each different filter has a different weights and looks for different features. So we have a 3x3, and say we have our big image like this. We have a 3x3 kernel, and it slides across the image. And for each image, it creates another feature map. So after this, we would have 32 feature maps. Yeah, okay. So then the filter, yeah, it looks for different things. So that's why not all the feature maps are the same thing, because they're gonna they're gonna be looking out for different things, different like textures, edges, and yeah, they're gonna have different weights. So then we have input shapes. Input shape is 32 by 32 image and 3 RGB channels. Then we have a pooling layer to reduce the spatial dimensions to 2. Then we have another convolutional 2D layer. So, layer to our neural network, convolutional neural network. So here we're gonna have 64 filters. So this means we have our 32 filters, 32 feature maps, just like this. And then what we're gonna do is we're gonna treat it as a 3-dimensional object. So we're gonna have 64 filters acting on each 3/3 kernel, and it's not just a 3x3 kernel now. It's going to be 3x3 by 32 because it's in the third dimension. So then we'll have 64 filters as a result of that. Then we'll also use a max pooling 2D model, as this is also a convolutional 2D model to reduce the spatial dimensions again. We're adding another convolutional 2D to have another 64 filters. So this will give us 64 feature maps and a 303 kernel. This is the kernel that will slide across the image, looking out for those specific patterns that are in the filter. Okay, so then we're going to flatten the dataset before we can pass it to the fully connected dense layers. Okay, now let's see. I'm just going to check OBS is still running. Yeah, okay, it is. So now we're going to use some dense layers. This helps improve the model. So we're having 64 units, like we did here, for better. It's just standard practice. And we have ReLU activation. We have ReLU for all of these. Just a reminder, ReLU, if a number it takes in is greater than 0, it just spits out whatever that number was. But if it's 0 or less, it returns 0. Okay, then we're doing the final layer is going to be a dense layer with softmax activation, because there are 10 different classes in the CFAR10 dataset, and softmax gives a probability for each of the 10 classes with our 10 output neurons. Okay, so then we're having Adam optimizer, sparse categorical entropy for multi-class classification, like in the CFAR10 dataset. Then we're going to train the model, 10 epochs. Validation data is X test and Y test, and batch size 64. Then we can print our accuracy, and we saw that we had good accuracy of 0.71. And yeah, for instance here, actual frog, predicted frog, showing that our model works. So yeah, that was day 11. Now let's look at day 12. So here we also using pretty much the same code before. So we're having 224 by 224 images. So this is a pre-trained model, ResNet 50. and accepts 224 by 224 images. So we're doing tf.image resized, and then we're let's see what we're doing here. Converts labels to categorical, so we're one hot encoding them in order to use for our pre-trained model. Base model, resnet weights equals ImageNet, include top was false. So here this is just like the boilerplate that we need for this model. We're just fine tuning the hyperparameters. Okay, and then we're going to add a dense layer and a global average pooling. So dense relo activation, and the final one is softmax, the same as we saw in the previous one where we just trained it from scratch. So we're making the model, and then we're going to compile it, and we're going to train it finally. Okay, so what it says here about unfreeze the last few layers of the model. Okay, so then we're going to unfreeze some layers, then we're going to compile it again, and then we're going to train it again, which helps the model's performance. Moving on to day 13, let's see what we've got. Okay, so here, something to do with stocks. I think this was the, I've forgotten the name now. They're neural networks that they're good for time, where the order of the sequence matters. So here we're creating sequence X train, Y train, train test split. And we're using the Apple data. Oh, long-term short-term memory. No, short-term memory. Which is, this is like more efficient because it doesn't have to go through the model and adjust the weights as often because we've got the memory. But it does require a bit more memory, which can sometimes be quite slow if you don't have enough RAM and you have to do using some of the like its secondary storage. Okay, so here we're going to create a sequential model, and we're having a LSTM layer with 50 units, and we're having one dense layer, and then we're going to compile the model and fit it, and then we're going to show our predictions. Okay, and that I'm not sure if this data was correct, but yeah, that's what our model gave us. So yeah, here we use the LSTM because we're carrying memory forward because we need that for the stock price. Like basically a bunch of LSTM gates. Okay, so now let's go on to day 14. Let's see what we did here. Okay, I think there's sentiment analysis using IMBD dataset. So here we're just getting the data from the movie reviews from the IMBD dataset, X train, Y train, and then we're going to pad sequences to ensure all reviews are the same length. And here we're also going to use, but first we're going to use an embedding to convert word indices into dense vectors. So 10,000 words into 127 dimensional vectors. And then we're going to have an LSTM layer to process the sequence of word vectors, and then we're going to add one dense layer with a sigmoid activation function. This gives a probability of whether it's either positive sentiment or negative sentiment. And then we're going to finally compile it with Adam and binary cross entropy for binary class classification and use the accuracy metric. Okay, and so here we're going to train it and show accuracy, which is 0.85, which is pretty good. And then we're just going to show that our accuracy is improving over time, and our loss is also decreasing. But it looks like we got a bit of noise in this one as it starts to increase for some reason, the validation loss. But anyway, okay. So yeah, so that was all for this one. So where we had embeddings, because we need to convert the words into dense vectors. So embeddings like just pre-trained, like word to vec and stuff like that. So we can actually use these words and like we can make these words into a meaningful type. So here we have like 10,000 words, so we convert them into 128 dimensional vectors, which the model can actually pass using the LSTM layers and the dense layers. Okay, so now on to day 15. So here, I think this was translating. Oh, English to French data. Okay. With input true. Tokenizer EN. Okay. So encoding and decoding. So this helps to find when we reconstruct it. If there's any errors in reconstructing it, this is a good way for like language translation, because if there are any errors, we'll know that it's not the correct translation. And if we just, this is called transformers, which use in many ML applications. So here we're just going to compile the model with Adam Optimizer and sparse categorical entropy for multi-class classification. And we're going to fit the model, which is basically training. Well, it is training. Okay, and then this is all just the code for building a transformer, which we can kind of just leave to chatgpt to do, as it's pretty much going to be very similar. We're just going to have to fine-tune our hyperparameters. And we're just implementing from scratch the multi-head attention, like self-attention, which is like finding which two features like are related to each other and which are important in our final output. So yeah, that's all for today's video. So thank you for watching, and I'll see you in the next video. Goodbye.